Hello, this is my Discrete Structures Homework 1. Let's start on question 2.3. So we're going to be finding the domain and range of the functions. Note that in each case, to find the domain, determine the set of elements assigned values by the function. So here is the first thing that we needed to do was a summary. So I just said, like, the question is asking me to find the set of inputs and of the function, the outputs, because inputs and outputs are basically the domain and range anyway. So here's two of the references that I used to help me with this question. I'm going to be probably putting the Google Doc up with me. I think I can like download it and then put it up with the video. So if you want to go click on those to help yourself easier, or like to see like some of the stuff that I looked, then that'll be probably a good thing. Um, so a brief description and assumption. So I'm gonna assume that the domain and range, they'll basically like change each other. So if the domain changes, like the range will change. Um, some of the key observations, that a bit is equal to like 2, 4, 8, 16, 32, 64. That was I think it was in one of these two links, I can't remember, from one of the ones I was looking at. And then a byte is a string of 8 bits. So now this is so we're going to show my work. So basically for A, I just had the domain is all real numbers possible in a bit string. So that would be, including, like, it wouldn't include negatives, because I don't believe um, they can be negative. They might be able to be negative if they are, all real numbers. And then the range is an integer. So B, it's the function that assigns in each bit string twice the number of zeros in that string. So the domain, and I think that is like all real possible numbers in the bit string, and then the range is non-negative integers, so all positive. I could have just said positive integers. That probably would have been easier, but it's fine. For C, the function that assigns the number of bits left over when a bit string is split into bytes. So the domain would be all real numbers in the bit string, and the range is going to be 0 through 7, because whenever it goes into a byte, I'm pretty positive that it you'll get it, like, it basically like takes away 1 from the 8, so which is why it's not exactly 8, it's 1, 0 through 7. So D says the function that assigns to each positive integer the largest perfect square not exceeding this integer. So the domain would be all positive integers, and then the range would be so this was talking about perfect squares, so I think it's going to be the perfect square integers, so like 64, 81, 144, because 64 is 8, 9, 12 is 144. It could also be 4, 9, because 3, and so on. So now a reason why I feel like this is the correct answer. So I believe that the solution, and I don't know if I'm supposed to be reading this. I'm going to be reading it anyway. I'm not for sure. I believe the solution that I came up with is the correct answer. I looked up multiple resources to help me out along the way, and I was pretty sure that, like, I was kind of confident in this a little bit because I've done this before in other math classes. I just needed to read up on it again a lot, honestly. Like, it took me, I think it was like an hour that I read up on it to be able to do all this. Let's go to question 6. So question 6 is going to be a lot like question 5, because they were from the same section. They're going to be about the domain and range. So we're going to find the inputs and outputs of the functions. So references, I used the references from question 5 on 6 because they kind of like went over the same topics. So I'm going to assume that this problem, like I said in 3 seconds ago, is going to be a lot like question 5, since we're talking about domain and range. So this is going to be, so A, so the function that assigns to each pair of positive integers. I put the domain as pairs of positive integers and the range as positive integers. B, I put the function that assigns to each positive integer is the largest decimal. So it's going to be positive integers, and since the domain is positive integers, there's not going to be any decimals. So they're going to be all whole numbers, so it's going to be 1 through 9. C, so the domain I had as all positive integers in a bit string, and the range is, I said we're all real integers, positive, negative, or 0. Gotta include 0 because I didn't know this. for some reason, but 0 isn't considered negative or positive. That's a fun fact if you didn't know it. So, that's pretty cool. I don't know why it's not. I guess it's like 0 is like neutral. I guess that's why it's like not positive or negative. So, you know. So question D, I put the domain is all positive integers. The range is the set of integers that are positive. E, the function that assigns the bit string of the longest strings of ones in the string. So the domain is set of all bit strings. Range is the set of strings that contain 1. A justification. So I don't know why this is all bolded, but so I think this is right because I use the principles in the previous questions to help me figure out and answer the questions in problem 6, which is why that's why I think it's the right answer. So 7, we're going to be finding the domain and range again. So a sentence or summary. So the question is asking basically to find the inputs and outputs. I know I'm kind of repeating myself on that, but I mean it's kind of what the domain and range is pretty much. So brief description. So I'm going to assume that I'm going to be doing what I did in problem 5 and 6. List of references. I actually forgot to add this, but I'm going to use the sources from the other 2 questions, and then let me make sure that's grammatically correct. Okay. So A. So the function that assigns to each pair of positive integers the maximum these 2 integers. So domain is the set of positive integers. The range is positive integers. The function that assigns to each positive integer, 0, 1, 2, through 9. So the domain is going to be all positive integers, and then the range is going to be 0 through 9. The function that assigns to a bit string number of times the block 11 appears. So basically, the domain is going to be all real integers in the bit string, and then range is going to be the set of all integers, or it could be 0 because 11 could just never show up. I think I might be wrong, but that's what I think. D, so I said the domain is the set of all real integers in a bit string, and then the range is positive integers and including 0. You can't forget 0. People, sleep on 0, but zero's a cool guy. Can't forget him. I don't know. Don't ask. I don't know either. A justification for this one. So I think my answer is correct. I mean, for the first 2, I was pretty confident in 5 and 6. So I think with just taking those principles that I used in those questions to help me on this one, I think it was pretty easy. So that's why I think it's correct. So this one, 2.4, these were like really, in my opinion, really easy because it was just like the 10 sequences. There were a couple that were kind of tricky, but I feel like these were probably the easiest in my opinion. That or the matrices. The matrices were honestly kind of fun, except for the last one. That one wasn't fun. But continuing on. So basically, we're just going to be writing the next 10 numbers. So these are 2 resources that I use. I know like people don't say like Wikipedia is never a good thing to use, but it really, I didn't know what into the exclamation point was. So I mean it's a factorial. So Wikipedia, sometimes it comes in clutch, not gonna lie. Because I honestly don't know if I would have been able to I wouldn't have had an easier time if I didn't see that Wikipedia page. So sometimes Wikipedia is pretty nice. So a brief description and assumption. So I'm going to just assume that the sequences will be able to be repeated 10 times. If they can't, then I think there's going to be a problem. And I don't know if it's going to be a problem with me. Probably with me. I was like, if this can't be 10 times, I mean, I just don't know. So this is going to be my work. So it's going to be showing the 2 sequences, successive 3 or more, preceding them. So it's just going to be 2, 5, 8, 11, just going up by 3. Pretty simple. So this one is just listing every positive integer 3 times. So it's just 3 1s, 3 2s, 3 3s, and then it'll stop at 10 because that's what the question wanted. So only 1 4. So this one, it lists all the odd positive integers in increasing order, and then they wanted us to do the odd digits twice. So 2 1s, 2 3s, 2 5s, 2 7s, 2 9s. So this is where like the factorial really came. So this is what I have for what in. So it would be in times, or it would be 1 times, yeah, it would be 1 times 1, which is 1, and then minus, and then 2 times 1, which would be 2, which would be negative 1, and then 1 times, or 2 times 1, which is 2, minus 2 times 2, which is 4, which is why it's negative 2, and so on and so forth. So then E, the sequence that begins with 3, where each succeeding term is twice the preceding term. So it's just multiplying by 2 every time, so we're just going up by double. So we're just 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48, 48 times 2, wait a minute. That's not, wait, is that what 48 times 2? Oh, wait a minute. Wait, did I mess that up? Where each succeeding term is twice the preceding term. That's what 48 times 48 is. 12 times, wait a minute. Okay. Should be 3, should be twice the amount. So 3 times 2 is 6. 6 times 2, 12. 12 times 24, 24. How did I get so like off here? Maybe I'm just, it's late. Maybe I'm missing something. Let's just go to F. The sequence whose first terms is 2, second term is 4, and the 16 is the sum of the two preceding terms. So 2, 4, 6, 10, 16, 26, 42, 68, 110, 117. Or 178, not 117, sorry. So G is the sequence whose nth term is the number of bits in the binary expansion of the number n. So it's 1, 2, 2, 3, 3, 3, 3, or wait, well, 1, 2, 2, 3, 3, 3, 3, 4, 4, 4. The sequence where the nth term in the number of letters in the English word for the index n. I was really tripped up with this one, but I think one of the sources that I used, it wasn't saying like, I was really, whenever it said like alphabet or letters in the English word, um, honestly, I just misread like whenever it said words, so I was like, what? And then I saw and I was like, oh, it's saying like 1, it has three letters in 1, 2 has 3 letters, and then 3 has 5, and then after I saw that, like, it was just really easy. So a justification of my answer. So I'm pretty sure this is right because honestly they were mostly pretty simple, because it was just either like multiplication, which is pretty basic, or like addition. I think the one that gave me the most trouble was probably G, because, or no, H, because I didn't really know like what it meant by English word, but like it's fine now, like whenever I learned it. Number 6, it's just basically number 5, where we just list the 10 terms. So 5 points, and a sentence is just, we're writing the next 10 numbers. So this is one of the references that I used. This one, a brief assumption, and so I'm just assuming that everything works how it should, because I was pretty confident with how 5 was. Um, so I'm pretty sure that everything should work. And then this is my work. So if we're doing this one where it's 10, and we're subtracting 3 from the previous term, so it's going to go 10, 7, 4, 1, negative 2, negative 5, negative 8, negative 11, negative 14, negative 17. That you're just subtracting 3. If I couldn't do that, I shouldn't be in college. If I can't subtract 3. Now, did I use a calculator to do? No, I didn't. I thought about it though. I thought it would be funny. Well, I probably shouldn't have even said that. I don't think, it's like, oh, he's an idiot. I'd be like, what? Probably not wrong. The sequence to nth term is the sum of the first n positive integers. So 1, 3, 6, 10, 15, 21, 28, 36, 45, 55. So I think the C is the sequence whose nth term is 3n minus 2n. So this is basically just taking like 3 times. Oh, okay. I thought I messed up. I was going to move something. It's just like 3 times 1 minus 2 times 1, which is 1. 3 times 2 minus 2 times 2, which is 2. And honestly, like if you wanted to, you could just, it's just basically n times itself. It's just n, pretty much. The sequence whose nth term is the square root of n. So because 1, 2, and 3 both have, like, they don't really have, I think the square root, I can't remember, like, I know, like, 1 is, of course, 1, but, like, 2 is, like, 1.4 something, so because there's no, we don't do the decimals, it's just 1, so basically once it gets, like, 1, 2, 3, and then 4 is 2, and then it doesn't go past 2 until, what is this, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is 3, and then 10 would be 3, 2. E is the sequence whose first 2 terms are 1 and 5, and each succeeding term is the sum of two previous terms, so 1, 5, 6, 11, 17, so on and so forth. The sequence whose nth term is the largest integer, whose binary expansion defined in section 4.2 has in bits, so it's 1, 3, 7, 15, 35, or 35, 31, 63, 127, 255, 511, 1023. G, the sequence whose term is constructed, so it's basically adding 1, then multiplying by 1, and then adding 2, then multiplying 2, then adding 3, then multiplying by 3, so on and so forth. So it's like 1, 2, 2, 4, 8, 11, 33, 37, 148, 155. So the sequence whose nth term is the largest integer, k such as k, which is factorial, is less than or equal to n, so it's 1, 2, 2, 2, 2, 3, 3, 3, 3, 3. I believe that this is correct because with a couple helps from some of the resources that I had, based on the prior problem, and I think let me see right here, that it helped me a lot, and I think it was pretty easy to do those after I looked at some of those resources. Number 7, which I think is the last one of this one. So find at least 3 different sequences beginning with terms 1, 2, 4, whose terms, so basically we're going to be making 3 rules to make the statement true. A list of references. I use the references from the previous problems to help me with this one, and I use the book to help me with some of the sequential terms, like the x equals 2 to the power of n minus 1. So I'm going to assume that the 3 rules that I made all work. I'll be sad if they don't, because me and a friend of mine, we worked on that for 20 minutes. I was like, okay, I can't think of another rule, and I was like, can you help me? And he was like, sure. I was like, thank you, Jacob. Shout out to Jacob. So first rule each. So we're just gonna be multiplying by 2. So 1 times 2 is 2. 2 times 4 is 4. 4 times 2 is 8, and so on and so forth. Each sequential term is a positive integer that is not multiples of 3. So it'd be 2, then 4, and then 2 times 4 is 8, but 3 can't go into 8. 8 times 2 is 16, and so on and so forth. And then x 2 to the power n minus 1 is another one. So I believe that these are correct because I already understood the material. It honestly wasn't that difficult for me. It was pretty easy to put stuff in sequential terms and everything, and I had little to no problem. Okay, so 2.6, question 3, find a b. I think I have the picture here. Yes. So we're just trying to find what does the matrix AB make. I used the book to remind me how to use matrices because I forgot, because I haven't used them for 4 years or something. Now I'm going to assume that all my work is done correctly because everything was nice and everything was pristine. So you can kind of see here. So AB. Sadly, you can't really see from the glare from my lamp. I don't know why I couldn't think of that. So you can kind of see right here that all this work that I did, and it all comes out, 3 plus, negative 1, 2, 2 right there, negative 2 plus 0, negative 2, so negative 2, 3 there, so on and so forth, that this is all correct. And I'll stay this a little bit so you can pause the video and look for a second, or do what you want and kind of go through. Okay. So justification for this. So I believe that this is correct because I got these answers. They weren't it was pretty easy. And I believe in myself. That's what I was told to put. Someone said to put you believed in yourself, and I was like, I did believe in myself. So this is another one. So question 4 is asking the same thing as question 3 to see what is AB. Find what AB is. So I use the reference from the previous question, just like the book and stuff. So this one, I'm going to assume that the answer is correct since I did all the work. It came out nicely, so you can see right here. A. Honestly, I don't know how many times I messed up with the one. There were so many 1s and 0s that I got lost. Not gonna lie. I was 0, 1. I was like, wait, which side am I on? It's kind of frustrating, but it was fine. Here's all of my work with this. You can kind of see. You can pause the video and look at it to make sure that it's good. So justification. This answer, I believe this is correct because I was pretty confident in doing these matrices. They were honestly pretty easy after we went over them in class, and I was looking at the book on how to do them too. So now question 5 it kind of was it was definitely harder. I find what number makes the matrix work, or I should say, yeah, it does say numbers. A list of references. I honestly I did use I don't know, Mr. Everett, if you're watching this, but I used your video because this problem honestly like kicked my butt a little bit. I think I tried to work on it for like 30, 45 minutes. I couldn't figure it out. And then I remembered that you put up on the uh, topic that we could watch that, and I was like, thank you. I need this so bad. And then so this is the work that I have. So basically going here, a negative 9 over 5, D's 4 over 5, C negative 1 over 5, and then B is negative 6 over 5. So justification, Mr. Everett, your video helped a lot. I went back and double checked to make sure that whenever I put those numbers in, if I got the right answer, and it was. And whenever that happened, I was like, yep, this is yep, you did it right. And I was like, yeah, this is a great answer. And that should be it for discrete structures homework 1. Thank you.